Hi everyone! Last time we talked about determinants of a 2x2 matrix is AD minus BC, and the inverse of a matrix exists if the determinant is not 0. So today let's continue to look at higher order determinants. So let's generalize to n by n matrix. So we could do the same kind of calculation for 3x3 matrix, which is a lot of work. And we will find the same conditions if A is row equivalent to the identity matrix, if and only if the inverse matrix exists, if and only if the linear system has a unique solution, if and only if the determinant of matrix A is not 0. So these statements are equivalent. Okay? And how to compute the determinants of a 3x3 matrix. So this is how we do it. Okay, so first of all, we assign some sign there. Okay, the 1 entry is always positive, and then plus and minus, they alternate. Okay, so here let's choose the first row cofactor expansion. And how we do it, we use positive A times the determinants of the submatrix by deleting the first row and the first column. So which is this? So that's why we have A times the determinants of this submatrix. And then we have minus B times the determinants of the submatrix by deleting the first row and the second column. So D, G, F, I. And then we have plus C times the determinant of the submatrix by deleting the first row and the third column, which is D, E, G, H. Oh, there is a mistake. This guy should be D, E, G, H. Okay? And it turns out this is only one of the 6 ways to compute the determinant. And in the 3x3 matrix, we can use any row or any column to do the cofactor expansion. Okay, so here we choose the first row to do the cofactor expansion, but we can choose the second row or the third row or the first column, second column, and third column. And what we do is you assign a sign, so the 1 entry is always positive, and then it alternates. So then this is negative, this is positive, this is negative, this is positive, negative, positive. Okay, if you choose one row and then you just like positive G times the determinant of the submatrix by deleting the corresponding row and column, and then minus H times the determinant of the submatrix, and plus I times the determinant of the submatrix. Okay? And we will do more example about this. Alright. So that's why for n by n matrix, there are 2n different ways to compute the determinant. So we can choose any row to do the cofactor expansion, and we can choose any column to do the cofactor expansion. Okay. So this is the formal definition. Let ith row cofactor. The ith row cofactor expansion is ai1 plus. Okay, so this is the following. And the capital Aij is -1 to the I plus 1 times Mij, where Mij is the determinant of the submatrix found after removal the ith row and the jth column. And the Aij are called a cofactor. Okay, Mij are called a minor. And similarly for the jth column cofactor expansion, we also have these followings. Okay. So now let's look at this matrix. We have 6 different ways to compute, right? And which way do you want me to choose? I'm gonna do 2 different ways, okay? But you can do all the 6, and you can see the final answers, the determinants you get in the 6 different ways will be the same. Okay, let's choose the second row, okay? Let's choose the second row. Remember, we first want to find the sign. The 1 entry is positive, and then it alternates, right? So this is negative, this is positive, then this is negative. Alright, and then so let's say this is A, and then determinant of A is, so we do -2 times the determinant of the submatrix by deleting the second row and the first column. So we have 1, -1, -2, and 4. And then we have plus -1 times the determinant of the submatrix by deleting the second row and the second column. So we have 1, -1, -2, and 4. And then we have -3 times the determinant of the submatrix by deleting the second row and the third column. We have 1, 1, -2, and -2. Alright, let's see. So we have -2, and then remember the determinants of the 2 by 2 matrix, we cross multiply, but we subtract. So 1 times 4 subtracts -1 times -2. Okay, and then we have plus -1, so minus cross multiply. 1 times 4, and then -2 times -1. And then -3 times 1 times -2 minus 1 times -2. Let's see. So we have, this is 4 minus 2. And this is also 4 minus 2, right? And this guy -2 plus 2, they cancel. Oh, so this is just 0. And so we have, let's see. 4 minus 2 is 2, -2 times 2 minus 4, and then -2, so the answer is -6. Okay, and here we're doing the second row cofactor expansion. Alright, let's continue. Okay, so let's see. Let me use a different color. Okay, we pick the second row. Now let's pick let's pick a different column. Which column do you like? How about the third column? Okay. So remember that 1 entry is positive, and then the sign alternates. We have minus and plus. So this is plus, this is minus, this is plus. Okay. So after we figure out the sign, let's start. And then we have plus -1, so -1 times determinant of the submatrix by deleting the first row and the third column. So we have 2, -1, -2, and -2. And then next we have -3 times the determinants of the submatrix 1, 1, -2, -2. And then plus 4 determinants of the submatrix 1, 1, 2, -1. Okay, cross multiply. 2 times -2 is -4. Minus -1 times -2 is 2. 1 times -2 is -2, minus 1 times -2 is also -2. And then here 1 times -1 minus 1 minus 1 times 2 is 2. Okay, so let's see. Negative 4 minus 2 is negative 6. And because of this negative, we get 6. And here, oh, they cancel. We just get 0. And then negative 1 minus 2, negative 3. 4 times negative 3 is negative 12. So the answer is also minus 6. Do you see the answer are the same, right? And so here we're using the third column cofactor expansion. Okay, I strongly recommend you to try to practice the other row or other column cofactor expansions and see whether you get minus 6. If you don't get minus 6, maybe there is some mistake. Okay. All right. So let's look at example 4. Compute the determinants of this 4 by 4 matrix. So 4 by 4 matrix, similarly, we want to pick a row or a column to do the cofactor expansion, and we would like to pick a row or column that contains lots of zeros. So look at this matrix. Which row or column has lots of zero? You see the first row, it has 1 0. But then, what happened? The third column, it has 3 zeros. So maybe we should do the third column cofactor expansion. So remember the 1 1 entry is positive and it alternates. Okay? So that's why, okay, we're going to do the third column cofactor expansion. So the determinants, let's say this is B, so determinants of B, here we're using the third column cofactor expansion. So we have positive 5 times the determinant of the submatrix by deleting the first row and the third column. So 2 minus 1, 3, 3, 8, 1, 4, minus 2, 7. Okay, and then you can see because all the others are zeros, so we just get zeros. Okay, everyone? Alright, so now let's continue. Okay, so 5 times. Here, we want to compute the determinant of this 3 by 3 matrix. Well, because we don't have zeros, so the difficulty when we pick different row or columns are the same. So we just pick the first row then. Then we know this is plus, this is minus, this is plus. We pick the first row. Okay. So now we have positive 2 times the determinant of the submatrix 8, 1, minus 2, 7. And then minus negative 1 times the submatrix 3, 4, 1, 7. And then plus 3 times the submatrix 3, 8, 4, negative 2. Is that okay, everyone? So common mistake is students will forget to put this parentheses. Okay, don't forget this parentheses. Okay, now let's see. Cross multiply but subtract. 8 times 7, 56. Subtract negative 2 times 1 is negative 2, but because of minus, so it becomes plus. Minus negative 1 becomes plus. Cross multiply 3 times 7, 21. Minus 4 times 1, which is 4. Okay, so we cross multiply, but don't forget we are subtracting. 3 times negative 2, negative 6, minus 4 times 8, 32. Okay, so this is 58, 2 times 58, 116. 21 minus 4, is it 17? And this guy, minus 38 times 3 is minus 3 times 3, 9, 3 times 8, 24, 114, right? Oh, 116 minus 114 is 2, so we get 5 times 19, which is 95. So the answer is 95. Okay, and in the exam you have to show all the work to receive credits. Okay, because in the exam you can use your calculator, and your calculator, if you use a graphing calculator, the graphing calculator has a matrix, and it can do row echelon form, or it can compute the determinants. So in order to receive full credits, you need to show all your work. Okay, and strategy to compute the determinants of a large matrix. So we can use row operation to transform the matrix to a new matrix with a lot of zeros, and we can keep track of how the row operation changed the determinants. So here we're gonna learn some properties of the determinants, but we won't go into very detail. Okay, so in exams, when I give you a matrix, you can just do the cofactor expansion to compute the determinants. Okay, so now let's roughly mention the properties. Number 1, multiply a row of A by a non-zero number K to get B. Then, okay, how do you get B is you multiply a row of A by a non-zero number K, and then the determinant is gonna be K times, so determinant of B is gonna be K times determinant of A. Because if you picked that row to be the cofactor expansion, then you will realize in that row, because all the entries you have the factor K, you can factor it out, and then you just get, this is the determinant of A. Okay, so this is the first property, multiply a row of A by a non-zero number K, then you get the determinant is K times the determinant of the original matrix. And similarly with, so this is not only row, you can multiply a column. So similarly, because you can do row cofactor expansion or column cofactor expansion, so it's the same idea. So, okay, column. Second property, interchange two rows of A to get B. Then the determinants, you get a minus sign. Why is that? Okay, remember you get so you get plus minus plus. If we interchange two rows or columns, let's see here. So okay, so if we look at the first row column in this case, then this is plus, this is minus, this is plus, this is minus, and then you will realize, well, the sign, you see the sign, they just change. The sign of one is positive, but the sign here is negative, so you will realize the determinant is going to be negative. So if you interchange two rows or two columns, then the determinant is going to be negative. Okay? And this is the exercise. Yeah, we can try to compute the determinants of A and B. Let's see what happens. So determinant of A is, let's see. So it's easy to use the last row cofactor expansion, right? Plus minus plus minus plus. So we have plus 1 times the determinants of the submatrix 1, 2, 3, 2, and cross multiply. 1 times 2 is 2, 3 times 2 6, which is minus 4, right? And how about determinants of B? We can also do the last row cofactor expansion, and so this is also plus minus plus minus plus. So plus 1 times the determinant of the submatrix 3, 2, 1, 2. Cross multiply. 3 times 2 6, minus 1 times 2 2, which is 4. Do you see? They are negative of each other. Okay, so this is the second property. The idea of the proof is use a cofactorial expansion about a row that has not been interchanged. Then one seems the minor or change sign. Yeah. This is the idea we talk about. Okay. 3. If two rows are identical, then the determinant is 0. So here is the proof. Suppose row L is the same as row K. We can define a new matrix B by interchange row L and K. By property 2, determinant of B is minus determinant of A. Because B and A are the same, because the two rows are identical, right? So determinant of B is also determinant of A. Now we get determinant of A is negative determinant of A. We can move this guy to the left, so we both sides plus determinant of A. We get 2 copy of determinant of A is 0, so both sides divided by 2, then we get determinant of A is 0. Okay, so right now we just briefly go over the properties. Okay, the main focus of our course for these properties will be property 6 and 7. Okay, so we go over property 1 to 5 quickly. Okay, 4. Suppose that the ith row of B is the ith row A1 plus the ith row A2, then the determinant of B is determinant of A1 plus A2. Okay, so let's look at this. Okay, look at the following. Do you see A1 and A2? So the first row of A1 and the second row of the first row of A2, and when we add them together, it becomes the first row of B. Okay, and then you can compute the determinants of them, and then you will realize the determinant of B equals the determinants of A1 plus determinants of A2. Okay, alright, so you can pause the video and check this out. Have you finished? Alright, let's check together. Okay, so what is determinants of A1? Okay, we choose one row or one column to do the cofactorial expansion. How about let's choose this one? So plus, minus, plus. So positive 1 times determinants of the submatrix 3, 2, 2, 6. Minus 0 times whatever is 0. Plus 5 times the... sorry. Okay, sorry. The first one, I should delete the first row. So we get 2, 6, 0, 3. And now we delete the last row. 3, 2, 2, 6. Yes. So sometimes if you see a mistake, please let me know, okay? Yeah, sometimes I also need to check my work because sometimes I could also make mistakes. So we need to be careful and check our work multiple times. Okay, so 2 times 3 is 6, minus 6 times 0 is 0. And then we have the 5. 3 times 6, 18. 2 times 2, 4. So 5 times 14. 5 times 14. 5 times 1, 5. 5 times 70. 76. Okay, everyone. So how about determinants of A2? Well, it's better to pick the first row because a lot of 0, right? Plus, minus, plus, so positive 1 times determinant of the submatrix 0, 2, 5, 0. 0 times 0 minus 2 times 5, which is 10. Okay, how about determinant of B? Let's also use the first column. So plus, minus, plus. So 1 times, oops, almost wrong again. 2, 6, 0, 3. 0, so minus 0, and then plus 5 times 3, 3, 2, 6. So 2 times 3, 6, minus 0, and 5. 3 times 6, 80, minus 2 times 3, which is 6. So this is 6 plus 5 times 12. 5 times 12 is 66. Okay, so you can see determinants of B, which is 66, equals determinants of A1, 76, plus determinants of A2, negative 10. Okay? Alright. So now we just do an example for the proof. You can read the textbook. If you have any questions, feel free to ask me, okay? So number 5, add a constant non-zero constant multiple by one row of A to another row of A to get B. Then the determinants of B equals the determinants of A. Okay? Proof. Let's see what happens if we add K times row 1 to row L to get B. Okay? So this is row 1. And let's see the matrix such that the L row C is K times row 1 of A. Okay? So the row L is the K times the row 1 of A. Okay? And then now you can see B, we are adding K times the first row of A add to row L. Okay? And then but it's like L row of A plus L row of C. Okay? And by the property 4, we know determinants of B equals determinants of A times plus determinants of C. Now define D to be this following, and notice that so D is you replace the L row of A with the first row of A. And notice that the L row of C is K times the L row of D. So that's why by property 1, determinant of C is K times determinants of D. And determinants of D is 0 because the two rows are identical. Okay? This is a property. If two rows are identical, then the determinant is 0. Okay? So that's why now determinants of A plus and determinant of C is 0. So that's why we just get determinant of A. Okay? So this is the proof. Okay, so 1, 2, 5, we just go over briefly. Now, the importance, which you will see a lot, is property 6 and 7. So property 6 and 7, please pay more attention to it. Okay? The determinants of a triangular matrix, is the product of the diagonal elements. So, for example, okay, what is triangular matrix? Triangular matrix. So this guy, the non-zero entries are on the upper triangular corner. Okay, so this is an upper triangular matrix, where the lower left corner are zeros. And then this guy, you can see the non-zero elements are on the lower triangular. So this is a lower triangular matrix. And now you can see the right upper corners are zeros. Okay, so here A is upper triangular, B is lower triangular. Okay, triangular matrix is like you have the diagonal elements, and then one side of it just contains zeros. Okay, so then the determinant is the product of the diagonal elements. Okay, why is that? So let's compute the determinant. Then you understand why. Okay, so let's look at A. Well, maybe it's easy to use the first column cofactor expansion, right? Because it has a lot of zeros. So then we have 1 times the determinant of the submatrix 2, 6, 0, 3. Okay, and because the other ones are zeros, so we just get zeros. And then now what happened? You cross multiply. So cross multiply 2 times 3, but because 0 times 6 is 0. Now, do you see we have 1 times 2 times 3? Wow, that is exactly the diagonal element of the matrix A. So that's why here we get 6, which is the product of the diagonal elements. How about determinant of B? Okay. Here we should use the first row cofactor expansion, right? So we have 1 times determinant of the submatrix 2, 0, 6, 3. And then now when you compute the determinant, you realize, oh, it's 1 times 2 times 3 because 6 times 0 is 0. Oh, what is 1, 2, 3 again? 1, 2, 3 are the diagonal elements. So that's why we also get 6. Okay, so this is true for all the triangular matrix. The determinant is just the product of the diagonal elements. Okay? And then the next one, determinants of the transpose matrix equals the determinants of the matrix itself. Because remember what is transpose? You just interchange the rows and columns. But so you imagine if we use the first row cofactor expansion of A, it is the same as the first column cofactor expansion of the transpose. So that's why they have the same determinants. Very easy, right? Okay. Now let's do some examples. Example 8. Look at the matrix A. Does AX equals B have a unit solution for any vector B? Okay, I want to remind you, do you remember we said the following statements are equivalent? First one, we know A is row equivalent to the identity matrix. Second, the inverse exists. 3, the linear system AX equals B has a unique solution for any B. 4, determinant of A is not 0. So all of these, the following statements are equivalent. So this question asks, does the system has a unique solution? Well, the easiest to check is to check the determinants. Is the determinant equal to 0? If yes, then yeah, it has a unique solution for any B. If no, then it has not there's a B such that it has no unique solution. Okay. So now let's continue. Okay, how do we compute the determinants of A? Alright, this is a 4x4 matrix, right? We want to pick a row or column which consists of lots of zeros. In this case, we can see the second row has a lot of zeros. And let's give it the sign. Remember the 1, 1 entry is always positive. And minus, plus, minus, plus. So then we see determinant of A is minus 1 times the determinant of the submatrix by deleting the second row and the third column. So 1, 2, 4. Minus 1, 2, 2. And 1, 1, 1. Okay? Now, we're going to continue. So, let's see which one is easier. Okay, you can use the first row cofactor expansion, but I want to do something different. I want to use the third row. Okay, let's use the third row because I see a lot of 1 there. Okay, so now we use the third row. We get positive 1 times determinant of the submatrix by deleting the third row and the first column. So 2, 4, 2, 2. And then minus 1 times the determinant of deleting the third row and the second column. So minus 1, 4, 2. And then plus 1 times the determinant of the submatrix. 1, 2, minus 1, 2. Okay, cross multiply 2 times 2 is 4. 2 times 4 is 8. 1 times 2, 2. Negative 4 times minus 1 is minus 4, but negative become positive. And 1 times 2 minus negative 1 times 2, so negative 2, so become positive. Yes, so be careful, the middle sign. We're doing cross multiply, but we are subtracting. Okay? So we have what? Minus 8, negative 4, minus 6 plus 4. Oh, you see they cancel? We get 6. So 6 is our answer. You can see the determinant is not 0, so yes. The system has a unit solution. Okay, so that finished this example. Alright, so let's continue in the next video. See you soon!